Hello folks, today I have a tool with me to demonstrate a certain concept. So the concept today I'm dealing with is stationary waves formed in a string under tension. So we have a string, it is under tension, which means it is stressed by some means, and we will form stationary waves there. And we will see what type of frequencies are possible, practically as well as theoretically. So to act as a string, I have got with me this tool which is called as a Slinky. See, I have been demonstrating this to students for around 18 years. So I got this from a student, 19 years ago or so ago. I just said in class that if such things are there, I can demonstrate waves. So one of the students volunteered to give it to me. Her name is Annie Shrestha. I don't know where she is right now. We're not even friends on Facebook. We used to communicate in Hotmails and Gmails, but not in Facebook. So wherever she is, I wish very good for her. So I've been using the device given by her for these many years. So in those days, I was not married. Later that I married, and it survived two of my children. They played with it a lot, but still it survived the mishandling or handling of both of those children. And now I think it will be a very good tool for them as well when they study waves and when they grow up. So this is a very flexible thing made of plastic. Material is plastic, but it's very flexible. As you can see here, it is just wobbling like that. So so when I do like this, every part of it comes under tension. So I don't need to stretch it like this. Even it is under tension under its own load. So let us see the modes of vibration of this thing. So if I extend it till here, and if I just apply some force like this, it will oscillate like this. So this oscillation is, when it oscillates, I can see one node at the very edge, another node here, and here it is anti-node because its vibration, the amplitude is very high. So at this time, it is in its fundamental mode. So that means what is happening here is the mode of vibration at this time is somewhat of this type. So if this is the string, these are the ends. So the mode of vibration is somewhat like of this type. And at that time, what happens is the length of this thing accommodates half of the wavelength of the wave so formed. Why half? Because it is only half of the wave. If it extends like this, it will make a complete wave. So it is 1/2 lambda at this time. And what I can do from here is, so lambda is equal to 2L here. So the lambda of the wave formed is twice into the length of this thing. Now if I increase the frequency, if I increase the intensity or frequency of vibration, what happens is it will start to vibrate like this. See, the mode of vibration has changed. Now we have node there at the very edge, node here in the middle, and node there. Then we have two antinodes here, you can see here. The central region has got the node. So now the mode of vibration is somewhat like this. So this is the end of the string, this is the end of the string, this is the middle. So it is somewhat vibrating like this. It is somewhat vibrating like this. So this is the modes of vibration. Here it is a node, antinode. And now we have a complete wave formed here. So that's why the length this time is equal to lambda itself. But now the lambda of a previous case and the lambda of this case, they are different. So I'll name it as lambda 1 and this as lambda 2, which gives me lambda 2 is equal to L. So this time the value of lambda 2 is equal to L. Previously lambda 1 is equal to L. Now from previous case, what I can obtain is frequency. So frequency is equal to velocity by lambda 1, which will be equal to velocity by 2L. and here I have got frequency is equal to F1 F2 equal to velocity by lambda 2 which will be equal to V by L. V by L, I can change this into 2 into V by twice L, and that's equal to 2 into F1. So the frequency in the second time is twice of the frequency of the previous, and you can notice this in the way I have oscillated it. For example, in the first case I did it very slowly like this. In the second case I had to make it faster. See, so this thing is definitely faster than the first case. So that's why the frequency of this time is twice of the frequency of the previous case. Now if I try to vibrate it even faster, so let us see what happens if I do that even faster. So see here, now I have got node there, node, and node. So I've got 4 nodes here, node, and antinodes are 3 here, antinode, and antinode. So 4 nodes and 3 antinodes, and the mode of vibration here is somewhat like this. So let us say this is the length which I enclosed, so it should be same. So let me do it here. So length should be same. Now what has happened is there are 2 nodes formed, so it should be equal to from here like this, and like this, from here like this, and like this. So I have got 4 nodes, n, and I have got 3 antinodes like this, and here this whole length accommodates one wave and the other half. So it's equal to 1.5 of the wave. So 1.5 of the wave will equal to 3 by 2 of the lambda so formed. So this is equal to lambda 3 lambda 3 is equal to 2L by 3, and it will give us frequency 3 is equal to velocity by lambda 3 equal to velocity by 2L by 3 equal to 3 V by 2L, and this V by 2L is equal to F1, so it should be equal to 3F1. So the frequency of this time is 3 times the frequency of the first case. Now if I go on vibrating it, I can have even more nodes here. So let me try. So individually I can try just one more step. So here I have to form 3 nodes here, 3 nodes and 4 antinodes. Let me try. 3 nodes and 4 antinodes here. Yes, so I'm doing it. You can see here, I can see node. So see here, I have done here. So node. It is 5 nodes, I suppose, 5 nodes and 3 antinodes here, 3 antinodes. So not only 3, I suppose 4 antinodes, because I have formed 5 nodes here. Let me do it once again. I lost the counts since the colorful display has made me lose the count. So see like this. So 1, 2, 3, 4, 5 nodes, and 1, 2, 3, and 4 antinodes in between, and it's pretty fastest among all of these things. So that's why now I'll have 4 of the antinodes, and 5 of the nodes, which will give, in this length there will be 2 wavelengths, 2 lambda 4 now should be different. So it will give us lambda 4 is equal to L by 2. So now frequency 4 will be equal to velocity by lambda 4 equal to velocity by L by 2 equal to 2 V by L. So it can be changed as 2, let us make it 4 V by twice L. So this will give us 4 into F1. V by twice L is equal to F1. So that's why we have this. So that means that we can form lots of nodes and nodes here, depending on how fast I vibrate it. So I'm a human, so my hands are stretched there, so I cannot do more than this. But if I get help from somebody else, I have done up to F5 in the classroom, done up to F5 in the classroom. So that requires tremendous effort from me like this. So that person will be stationary there. I make the effort. So when I make the effort, I have done it up to F5. So this demonstrates the formation of stationary waves in a stretched string. And as you know, these things are very much useful in the design of bridges, how to make them safer, in the design of buildings, how to make them safer, or this can be used to make certain other things which have to be oscillated or vibrated more than required by use of proper things. Say, if you see here, the antinode portion vibrates a lot and the node portion does not vibrate. So at the node, amplitude is zero, almost zero, and at the antinode's amplitude is highest, and so on. So this thing is useful in the design of several structures, whether they have to be made stronger, safer, or whether they have to be made in such a way that they break easily, and so on. So, this I think clarifies how we can demonstrate stationary waves that forms in strings which have been stretched.